Hi everybody and welcome to Six Sigma and Processi Produttivi YouTube video channel. This is my third video in English, and after having explained the normal distribution and its statistical meaning, this tutorial is about two fundamental parameters of the normal distribution, the mean and the standard deviation. This is the introduction slide. And let's go with the next slide that introduces the mean and the definition of the mean. Given a set of numerical values, it is the sum of all the values divided by the quantity of them. The formula is represented here, where m is the mean. At the numerator, we have the sum of the values of a distribution represented by x, x1, x2, up to xn. And at the denominator, we have the number of the values, which is represented by n. The numerator is also expressed by this term, which stands for the sum of the x values indexed by the letter I, where the letter I ranges from 1 to n, which is the number of the values in a distribution. Let's make immediately an easy example, which is, as we said in the introduction tutorial, is my main purpose, to explain in an easy way with easy and practical examples. So if I have 5 pressure values, for example, the values of pressure of gas cylinders, 10, 15, 25, 18, and 22 bars, the mean of these 5 values, which are called the values of a distribution, is given by the 5 values summed together, so 10 plus 15 plus 25 plus 18 plus 22, divided by the number of values, which is 5, and the mean is 18 bar. Let's go then to the standard deviation and its definition. In this case, the definition is a simplified definition. It's not the mathematical precise definition, because my purpose is to simplify definitions to immediately explain the concept, to immediately make you understand the meaning of the statistical terms. So, given a set of numerical values, the standard deviation provides a numerical representation of the spread of said values around the mean. In other words, it tells us how distant are the values from the mean. The standard deviation is a number, and so low value of the standard deviation means that all of the numbers of the distribution are close to the mean, and there are no values or only few values with values distant from the value of the mean, while a high value of the standard deviation means a huge spread of data around the mean. So where I have values very far from the mean on the right of the mean, so higher than the mean, and on the left side of the mean, so lower than the mean. This is the formula. The formula of the standard deviation is represented by the letter Greek sigma. It's a square root of a numerator and a denominator. The numerator is again the sum expressed by the symbol of square terms, where each term is the difference by the mean of the distribution and the single value of the distribution. There will be a number of square terms that must be summed all together, equal to the number of the values of the distribution, divided by the number of the values of the distribution minus 1. But let's go again to an easy example. Again, the same 5 pressure values used for the mean. You can see the numbers here, 5 terms. This is the formula represented again, where m, okay, is the mean. So we have to replace this letter with the term 18. Now we have to calculate the numerator. So try to sum each of these square terms, where xi is the number of one value of the distribution, and the value of the distribution, the values of the distribution are 5, and are these 5 values. Okay, well, there are 5 values, so there will be 5 terms, 1, 2, 3, 4, 5 terms. Each term is squared, as you can see here. Each term is given by the difference between the mean, which is 18, so you can find 18 here in the first term, 18 here in the second term, 18 here in the third term, and so on. And in the first term there is 10, as you can see here. In the second term there is 15, as you can see here. In the third term you can see 25, as you can see here, and so on. So the first term would be minus 8, but this minus is neutralized by the square, so we have 8 squared, then minus 3 here square, so 3 squared, and so on. So we sum all of these terms and we get a numerator of 138 that goes here. Okay, let's go on with the example. We have to divide by the denominator, which is n minus 1, but the terms are 5, so n is 5. 5 minus 1 is 4, so we have to divide 138 by 4, and we get 38.5. The square root of 34.5 is 5.87. So 138 divided by 4 gives 34.5. The square root of 34.5 is 5.87, and 5.87 is the standard deviation of these 5 numerical values. In the meanwhile, I can provide you with the definition also of 2 other statistical terms which have their relevance in the ideal normal distribution. The mode is the definition is again a simplified definition to make you immediately realize the concept, the meaning of this term. Given a set of numerical values, it is the most frequent value of the set. This is the formula, a little bit complicated. I won't spend time to explain the formula, but I will go again to the example because I want you to immediately understand the concept. And if I have 5 pressure values, not the same as before, I have changed the value 22 with another 25, so that I have 4 values, 10, 15, 25, and 18, but only the 25 presents twice. It has the highest frequency, while all of the other 3 terms, 10, 15, and 18, present only once. So what is the mode? The mode is 25, because among the 4 values it is the most frequent value, so twice versus once. And the median, again a simplified definition. Given a set of numerical values in increasing or descending order, it is the value in the middle. This is the formula of the position. Again, I won't spend time on this formula, but I will make an easy example. So again, the 5 original values, those used to calculate the mean and the standard deviation, so 10, 15, 18, 22, and 25. The values here are already ordered in increasing order. And the value in the middle is exactly 18, because there are 2 values on the left side, because lower than 18, and 2 values on the right side, so higher than 18. So the median is 18. There is a nice pictorial representation here of the median, the mode, and the mean in the context of an ideal normal distribution. What is an ideal normal distribution? Well, an ideal normal distribution is given by a mathematical formula, and it consists of an infinite number of data. This is very important. While the 5 values of the distribution, 5 pressure values of gas cylinders that we have seen before for the examples of mean, standard deviation, mode, and median were 5 values of a real distribution. So don't confuse an ideal normal distribution, which is the one you are seeing now, versus a real normal distribution. In the context of an ideal normal distribution, mean, median, and mode, so mean, median, and mode, match perfectly. They are the same number, and they are exactly the center value of an ideal normal distribution. Why? Well, let's talk first of the mode. The mode is the number in a distribution with the highest frequency. Well, we know that the y-axis of an ideal normal distribution represents the frequency, and the top frequency is the highest value, and the highest value in an ideal normal distribution is exactly in the center. So that's why the mode is in the center, because it is the number with the highest frequency. While the median is in the center, because the median is in a set of numbers in increasing or descending order, is the number just in the middle. But the ideal normal distribution is completely symmetrical, as you can see by the shape. And the center value divides perfectly the curve into portions equal. So 50% of the data are on the left side of the center value, and 50% of the data are on the right side of the center value. So the median is exactly the center value. Why the mean is the center value? Well, because don't forget that the ideal normal distribution consists of an infinite number of data. So there is always a number here. If I take a number here, which is on the right of the mean, and it is higher of the mean by a quantity of x, there is always the same number on the left of the mean, which is lower than the mean by the same quantity of x. These two numbers, if summed together and divided by 2, give exactly the mean. Since this statement can be replicated an infinite number of times for all of the values on the right and all of the values on the left, the mean is exactly in the center of the normal distribution. Let's talk now about the standard deviation in the context of an ideal normal distribution. I just said before that sigma, so the standard deviation, is a number, and is a number on the x-axis. This segment is sigma, plus sigma, because it's higher than the mean, and it's on the right of the mean. Minus sigma, it's the same value on the opposite side, okay? So it is lower than the mean, in the sense that it lowers the value of the mean. In this sense, it increases the number of the mean. It increases the value of the mean. This segment, so plus minus sigma, with respect to the mean. So if I consider the mean, which is in the center of the normal distribution, and I consider the range given by the mean, plus 1 sigma and minus 1 sigma, this range includes a portion of the curve, okay? The portion of the curve is given by these two vertical lines, okay? These two vertical lines, I can consider this value here and this value here, okay? in a vertical array, it will strike the curve in these 2 points, okay? And if I consider the area of the curve which is included by these 2 vertical lines, so at the end by the range given by the mean plus minus 1 sigma, the area included by these 2 vertical lines, this area contains a given percentage of data, a percentage of data with respect to all of the infinite numbers of the ideal normal distribution. And we will see this percentage of data included by this portion of area in the next slides. But let's first explain the differences in the shape of the ideal normal distribution given by a different value of the standard deviation. You can see ideal normal distribution, a Gaussian curve here on the left, and you can see ideal normal distribution on the right. The shape of the 2 curves is different. This normal distribution on the left is taller and tighter than the one on the right. Why? Because of the value of the sigma of the standard deviation. In this case, you can see that we have a low sigma, okay? A low sigma, if you remember my previous explanation, means a low spread of data around the mean. So it means that all of the data, in this case an infinite number of data, most of the data are around the mean. So there is a lot of values around the mean, and a lot of values around the mean means that the frequency is high. So the curve is high, okay, because of the high frequency of a lot of numbers around the mean, and it's tight. Why it is tight? Because if I have a lot of numbers around the mean, I will have only few values far from the mean, both on the right and on the left. Few values means that here the frequency is low, okay? So there is a dramatic drop of the frequency as I depart from the mean on the right and as I depart from the mean on the left. So the curve at the end is tall and tight because of a low sigma. But if I take the curve on the right, here I have a high sigma, because this segment is pretty higher than this segment. A high sigma means a high spread of data around the mean, so it means less values around the mean, and the frequency of the values around the mean is lower, okay? And the frequency is lower, it means that this curve is shorter than this one. But at the same time, less value around the mean means more values far from the mean. So the frequency here and here as I depart from the value on the right and as I depart from the value on the left means higher frequency. So the curve is also larger than this one. So low sigma means a Gaussian curve, tall and tight. A high sigma, higher sigma means a Gaussian curve, short and large. But if you remember, I was talking about the area included by a range of the mean plus minus 1 standard deviation, and it can be easily represented here. This orange area is the portion of area of the ideal normal distribution included by the range given by the mean plus 1 sigma and minus 1 sigma. The percentage of data in the ideal normal distribution, so made of an infinite number of data, included in this area, is given by 34% on the left and 34% on the right. So at the end, 68% of the data of the entire set of numerical values of the ideal normal distribution is included in this interval, 68% of data. But if I extend the range and I consider the mean plus 2 standard deviation on the right and minus 2 standard deviation on the left, I include 2 additional portions of 13.6% of data. So at the end, a range given by the mean plus minus 2 standard deviation will provide a percentage of data included in that portion of area of the entire set of values of the normal distribution of 95.5%. And the summary is here. So the mean plus minus 1 standard deviation is around 68% of the data of the entire set of data of the normal distribution, which is an infinite number for an ideal normal distribution. The mean plus minus 2 standard deviation includes the 95.5% of data of the entire set of data of an ideal normal distribution, and the mean plus minus 3 standard deviation includes the 99.7% of data. But these percentages are perfect mathematical numbers if I'm talking about an ideal normal distribution that is made of an infinite number of data. In the real normal distributions, things can be a little bit different, but let's see if these numbers are only theoretical percentages or if they have a practical meaning. Do you remember the 5 pressure values used before? You can see the 5 values of gas cylinders shown before, so 10, 15, 25, 18 and 22 bars. You remember the mean was 18 bar and the standard deviation was 5.87. We can round it to 6 bar. So the first range, so the mean plus minus 1 standard deviation is 18 plus minus 6. 18 minus 6 is 12. 18 plus 6 is 24. So the range from 12 to 24 does contain the 68% of the values, the 68% of these 5 values. Okay, the 68% of 5 values would be a decimal number. Okay, and so it would be 3 point something else, but we can round it to 3. So at the end, the question is, are 3 values of this set of 5 real numbers included in this interval? And again, if I consider the second range, the mean plus minus 2 standard deviation, so 18 plus minus 2 times 6, so plus minus 12. So 18 minus 12 is 6, 18 plus 12 is 30. Does this interval from 6 to 30 contain the 95.5% of the values of these 5 values? Okay, the 95.5% of these 5 values would be a number around 5, so 4.7, 4.8. But we can round it considering that all of the 5 numbers should be included in this range. Is this the truth? Let's see this in this pictorial representation. So we have here the 5 numbers, and this is the first range from 12 to 24. So what is the expectation? That 3 of these 5 values fall within the range. 10 is outside of the range because it is minus 10, 12. 15 falls within the range. 18 falls within the range. 22 falls within the range. 25 is outside of the range because it is higher than 24. But we have 3 values out of 5 within the range, and this is the expectation, exactly 3 out of 5. So the 68% percentage is okay, even if we weren't talking about an infinite number of data, but just 5 real data. What happens with the 5 values with respect to the second range, which is the mean plus minus 2 standard deviations, so a range between 6 and 30? The expectation is that all of the 5 numbers are within the range, or just a number slightly, very slightly outside of the range. But 10 falls within the range. 15 falls within the range. The same for 18, 22, and 25. So at the end, the expectation was that all of the 5 values of this real distribution fall within the range. And that's exactly what we got. There all, this tutorial is finished. I hope you have liked it. If you have liked it, please put a like in YouTube. Don't forget to subscribe and stay with me also for the next tutorials, because we will exploit the knowledge that now we have on the normal distribution and on its fundamental parameters, the mean and the standard deviation, to try to introduce the basic concepts of the statistics applied to the production processes. Now we are ready to introduce a concept like CPK, PPK, and so on, the normality of data, and so on. So thank you for being with me. Thank you for having stayed with me with this tutorial. See you at the next tutorial. Bye bye.